this chapter, we're going on to electricity. We're beginning our discussion of electricity and magnetism, beginning with the concept of electric charge. We'll get a bit of historical background first. Electricity, or the effects of it, had been known since antiquity. In fact, the word electron comes from the Greek word for amber, which is fossilized tree rosin. And amber, which had been used in jewelry, had been noticed that if you rubbed it, especially with, say, wool, that it, well, as we would describe today, it picked up a static electric charge. You could feel the hair on your arms being repelled by it, for example, and little pieces of paper or other kinds of materials would be repelled. So, it had also been found that if you took a glass rod, these days, by the way, we normally deal with plastic, which has similar properties. So, rubbed with wool, there. But if you take glass, and instead rub it with silk, you would find pretty much the same things happening. But if you took that glass rod that you'd rubbed with silk and you put it very close to a plastic rod or amber rod rubbed with wool, they would attract each other. On the other hand, two plastic rods rubbed with wool would repel each other, and two glass rods rubbed with silk, as a tongue twister, would also repel each other. Now, this by the 16 and 1700s, this led scientists to conclude that there were two different kinds of electric charge, and it was Benjamin Franklin who came up with the first real understanding of this. Franklin decided to assign, let's see here, actually I forget which one it is, because we don't really use the glass versus amber distinction that much these days. So he said, all right, if we have two different charges, it appears that we can add the charges, and if they're the same kind of charge, then if I rub a glass rod with silk twice as much, then I get twice as much of this kind of charge. If I rub a plastic rod or amber rod twice with wool, I get twice as much of that kind of charge, the opposite kind. Since they opposite kinds attract each other and like kinds repel each other, then this implies that they are that they really are opposite. And because I can add them and subtract them, well, if I take the glass rod and touch it to the plastic or the amber one, then things seem to have canceled out. So this implied that we could use the positive and negative symbols. We can add and subtract the charges. So he assigned the positive charge to the glass rubbed with silk, and then the negative charge to the amber or plastic rubbed with wool. Now, as we understand it today, the origin of electric charge comes from the atom, which was still not well understood in Benjamin Franklin's time. So in the atom, we now know that we have a nucleus, a concentrated spot of positive charge contained in the protons, surrounded by a cloud of negative charge, which are the electrons. Now we tend to think about the electrons orbiting the nucleus in circular orbits of different sizes, but that was a very early primitive quantum mechanical view. Now we have a more advanced view where it's more of a cloud of where the electrons are. Okay, so we have negative charge surrounding positive charge. Okay, the electrons and the protons are not the only components of an atom. You also have neutrons, at least in some atoms. But the neutrons, as you might infer from their names, have no charge. They are electrically neutral. So it's the electrons and protons that give rise to the charge that we experience. Now, an atom in its normal form is electrically neutral, and yet it has both positive and negative charges. That's because, as I said, these can be added together. And the positive and negative signs in this case cancel each other out. So the net charge we'll use the letter Q for charges in general. So not necessarily just the net. Maybe I should just say net here. Q is going to be the difference between the number of positive charges and the number of negative charges. So if I have capital N sub plus for positive charges, times the amount, the number of the protons in there. Now, the charge on a proton or an electron, we use the letter E for that. Now, the E really comes from the electron, which carries a negative charge, but we're going to deal with. Now, really what's moving around in the glass, the silver, the plastic, and the wool are the electrons. Those are what we can pull off the atoms. That wasn't known for, well, certainly well over a century after Benjamin Franklin. So we deal with this fact that we're mostly talking about what the electrons do, despite the fact that they have a negative charge, and we default to a positive charge whenever we do the math. So the amount of charge contained in an electron is exactly the opposite to the amount of charge contained in a proton. Opposite sign, but the same magnitude. So we use the letter E. E is the fundamental charge. And, though your book takes a while to actually tell you how much that is, let me get the actual number here. 1.6 times 10 to the negative 19th coulombs. Capital C stands for coulombs. Monsieur Coulomb was the one who had done the work on that part there, or a lot of work in early electricity, so it's named for him. Coulomb then is simply a certain amount of electric charge. It is not based on length or mass or time, which most of our other units are. It is separate in this way. So think of it as counting charges. Okay, so the protons have a positive E charge, and the electrons have negative E. So the net, Q, is the difference between the number of protons, N plus, times E, minus the number of electrons, N minus, times their charge there. So the net charge is just the number of positive charges, protons, minus the number of negative charges, all times E. Okay. So, if an atom has the same number of protons and electrons, then it is electrically neutral. Its net charge Q is 0. On the other hand, if you pull an electron off the atom, it would have fewer electrons but the same number of protons, giving it a net positive charge. You could pull 2 or 3 electrons off and get an even greater result. This gives you an ion, which is a charged atom. That would give it a positive charge. If you were to stick extra electrons onto it, you would make it a negative ion. Okay, now, how do the charges move around? Well, it turns out that we conserve the total amount of charge. In fact, the entire universe has all the charge it's ever going to have. And we will not create nor destroy electric charge. So there is a conservation of all the charge in the entire universe. And, what more is interesting, it appears that the entire universe is electrically neutral. So, possibly, likely, it seems that the entire universe has exactly the same number of positive and negative charges. But we can move those things around. Now, we have, in moving them around, in some materials, let's say like the plastic, the amber, the glass for that matter, an eraser, cloth, they do not let charge move through them, and they're called insulators. In an insulator, which you might think of as the normal behavior of materials, charges are bound to the atoms, and the atoms are stuck in place, at least in the solid. And so charges just, if you put extra charge on a piece of plastic here, if I deposit an extra electrons there by rubbing it onto them, then rubbing it off on whichever, wherever they stick to, they will stay stuck there. On the other hand, you have conductors, like metals, or ionized water, or water with salt and other minerals dissolved into it. In a conductor, the the electric charge is free to move about. Now, how it works is different in a metal than in water. In a metal, like this tray here, it turns out that when you take the atoms of a metal, those are supposed to be the nuclei and the electron clouds around them. The outermost layer of electric charges are free, are not tightly bound to the atom. And when you stick them all together into a solid, all the atoms together into a solid, those outermost electrons can just kind of wander around through the rest of the metal. So, that's why, if you have leather shoes, say, and wool pants, great for building up electric charge. So if I were on a dry day to scoot across the carpet like this and build up a static electric charge, if I touch the metal tray here, today is hot and humid so it won't happen, but I would get a spark. The electricity would jump over to the metal there, and what would happen, static charge going into a conductor spreads very quickly through the entire conductor. This is because like charges repel, meaning the same kind of charge, negative and negative for electrons, positive and positive for protons. Similar charges repel each other. So the electrons push them, the extra electrons push themselves as far away as they can from each other on the conductor. So if you've got a big slab of metal there, say of steel, and you put some negative charges on it like that on one side, they push each other away from each other and move to the outermost edges as far away as they can get from each other and fairly evenly distributed, which depends on the shape though. But they'll stick to the outer edges as well. They don't go into the material because they can always move farther apart if they're inside the material. And there's some other reasons as well. Okay, but you can't do that with an insulator because they can't move freely through it. If you stick extra charge onto this plastic, it will stay put. Okay, now we can test for what's happening with charges that we have built up with an electroscope. An electroscope is an instrument made with a metal rod that goes down and has hinged bits of gold leaf or other, like aluminum foil can kind of work. Little thin flaps, like here, that are hinged. Now, we usually put this in a jar so we can keep dry air in there because moist air carries the electric charge away, and it will discharge this. By the way, I forgot to mention, in conductors, in water, pure water is really not, distilled water is not a great conductor. But if you dissolve salt or other minerals into it, you get ions, electrically charged ions that can move around in them, and that's how the charge distributes. So that's what makes water a better conductor. Now, an electroscope. This is all a single piece here. It's metal, 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 metal. and so the charge can be conducted. So if you put extra charge on this, it will distribute all through this, and because similar charges repel, those little gold foil leaves push each other apart like this. And you look to see what the leaves of the electroscope are doing, and that tells you that there is an excess of charge. Okay, now, it turns out that we can do that even without adding extra charge onto the electroscope. Let's say we take a glass rod. Let's see here. Actually, not the positively charged rod. And if I put this, there's the rod. It's got positive charges on it, like that. So what happens? Well, similar charges attract, like charges repel. You have electrons free to move around on this. Negative charges, electrons, are attracted to the positive. So they will cluster up here. Negative. Close to the positive rod. Now, because the electroscope has the same amount of charge always, if the negative charges are up here, that means you've got extra positive charges at the opposite end. Okay, down like that. And because now this side is positively charged, the leaves move apart. And it could go the other way around with negative charges. Okay. Now you can even, this is called polarization. Polarization is the separating of positive and negative charges on a material. This can even be done with atoms themselves. In an atom, where you have the positive charges in the nucleus and the negative charges in the electrons in the cloud around them, what if you take a lot of extra positive charges over here? Now, the electrons are attracted to them. Now, they're attracted more strongly to their own atom's nucleus, but they'll also be attracted to this one. And so this cloud gets stretched out this way, like this, leaving this atom polarized. It's got more positive charge at this end and more negative charge at this end, but it's still electrically neutral. So with an insulator, where the charges are not free to move about, the atoms and the molecules as well are able to be polarized. So if you put a strong electric charge near it, you will wind up attracting that insulator because this external source of charge has polarized the insulator. And then now, this electric charge here pulls towards that, and that pushes away from it, but it's farther away. So what the force is stronger the closer the two charges are. Okay. Now, if the force between these, I mean, we can see that these attract, that they bring them together. So there's a force. The force then can be described mathematically by what's called Coulomb's law. So if I have two charges, Q1 and Q2. Now, they could be, positive 3e or negative 5e or whatever. E being the fundamental unit of charge, and then a number on that could be positive or negative, but how much? What are the forces exerted by charge 1 on 2 and by 2 on 1? Turns out you got the same force but in opposite directions. So the force between them, the force exerted by 1 on 2, the book uses a notation that's not standard. Because it's just introducing this, then they're trying to help you. But normally we would call this the force exerted on, the force onto exerted by number 1. It's not 21. If you had 21 sources, then you'd have to think of relabeling it. But force onto due to 1 is going to be equal to some constant, capital K, times Q1, Q2 over the distance between them squared. Now let's put absolute value symbols around the Q's, and we're going to give a direction. Let's see. Oh, and that's also equal to the force exerted by 1 on 2. Well, the magnitude is the same. Let me see how to write that here. Yeah. Force on 2, force exerted by 2 on 1, we normally write force on 1 due to 2, same amount. And that's called Coulomb's law. Now, the magnitude of, the magnitude is given here. The direction is, if, let's see, Q1 and Q2 have the same sign, the force is directed away from each other. If they have the opposite sign, they attract. And they attract or repel along the line that goes straight through them. We'll do this more mathematically rigorously in a moment. Now, this capital K is called the electrostatic constant. And it's 8.99 times 10 to the 9th power newtons meters squared per Coulomb squared. Okay, electrostatic constant. Now, if you take a look at this, you'll realize that this has almost exactly the same form as Newton's law of gravity. Negative capital G, I'm running out of space there. Negative capital G times the mass of one object times the mass of the other divided by the distance between them squared. Exactly the same form. We'll get with the negative sign in a moment, but remember that gives you the direction that the force is pointing. And I'm giving it to you here in a more complicated way, which we'll tidy up later. But it's got, instead of charge, Newton's law has gravity, has mass, and instead of the gravitational constant, this is the electrostatic constant. That's a comparable thing. Now we need to put in a different form of this. So let's see. If K is the electrostatic constant, let's define epsilon naught. Epsilon subscript 0. That's a lowercase epsilon, not an E. It's got like a C with a slash through it there. It is the Greek letter E, though. This is called the permittivity constant. And it has a value of 1 over 4 pi k. That's a capital K, but I shouldn't put the surface there. And that means it's equal to 8.85 times 10 to the minus 12 Coulomb Coulomb squared per Newton meter squared. Yeah. So, writing in terms of the permittivity constant, well, let's see. With the electrostatic constant we had, that form, and giving only the magnitude value. In terms of the permittivity constant, it's 1 over 4 pi epsilon naught times Q1, Q2 over R squared. Okay. Which of these you use is arbitrary, but there are some applications where the electrostatic constant is more useful if you're measuring the force. If you're doing deep things with electric fields and so on, you might be dealing with the permittivity constant or with electromagnetism or light waves. Okay, a couple of notes. Either one of these, this force only applies to point-like charges. Infinitely small. If we have a distribution of charge, then we have to add up all the forces acting on another one there, or integrate over the distribution of charge. Secondly, the forces can be added. They can be added like any other kinds of forces. So you just do the vector addition with that. Okay, next I want to get to the idea of an electric field. The electric field really goes back to the magnetic and electric and magnetic fields. This goes back to Michael Faraday, who lived in the late 17 and early 1800s. Now, he had gotten a late start on his education, and he never really mastered mathematics. And if you look at his notebooks, there are mastery of scientific work, but no math, no equations, really, or very few. I've always heard it was no math. But his measurements then did a more pictorial, graphical way of expressing things. And it's to him that we owe the idea of the electric field. So, if you played with a magnet, thing we did in elementary school with a bar magnet, for example, which has a north and south end, and if you take a sheet of paper and iron filings over the top of that, sprinkle the iron filings, they will line themselves up. I'll just draw out like this here. Like this. Now, Faraday, working with electricity, had worked on the same kind of description of the electric charges. Now, Newton, in his description of how forces work, was kind of vague on how the force of gravity is transmitted. What is the mechanism? He had said, hypotheses non fingible, which is Latin for, I'm not going to feign hypotheses. I'm not going to try to get into the explanation as to the physical reason why, but I'm going to describe how it happens instead. Leave it to the philosophers to ask why. The philosophy then being mostly indistinguishable from the other areas of science. But he was opposed by others who thought that this was a, quote, spooky action at a distance, you know, kind of an occult sort of force. How can it be transmitted with no direct contact? Like billiard balls bouncing off is easy to see why. They touch them. But how does the Earth attract the moon? For the same reason, you might say to Faraday, how does a positive charge attract a negative charge? Or how do two negative charges repel each other? And he would say that instead what happens is that if you have a positive charge here, that it creates an electric field. Let's see here. I'm not going to put arrows on it there for a moment. I really should, though. We don't get into the vector description of it until a bit later. Yeah, okay. Nope, that is true. Now let's put another positive charge over here. It experiences, so the first charge creates a field around it. Now the field means that there are values of this field. It's got a certain strength in different places in space and a different direction given by these arrows. So if you get farther away, the field is weaker, the arrows get shorter. You get still farther away, it gets even shorter still, and so on. Now, if you put another charge out here, it doesn't talk directly to the first charge. It instead experiences the field created by the first charge. Of course, it creates its own field, which is experienced by the other charge. And a charge does not experience its own field. It doesn't exert a force on itself. So, the charge creates a field surrounding it through space. It affects space. And then the field is what the other charge interacts with, and that causes the force. That's how a force can be transmitted over a distance. And we can do the same thing with the force of gravity. There's a gravitational field surrounding objects that have mass. All right. So, if we want to know what a field looks like, let's say we don't already have the answers. I mean, the work has been done by scientists for hundreds of years now. But if we were trying to find out for the first time, we would take a source of charge. This is our source. It creates the field. And we use the field, electric field, capital E. Remember, we're using the lowercase e for the fundamental unit of electric charge. Now, if we put, to see which way the field is pointing, we would put a charge out here. Let's use a positive source, and we'll put a small amount of test charge. There. We're going to call that Q. That's our test charge. And we'll see which way it moves. So we'll find out what force is exerted on it. So, in this case, positive charge, it's going to move away that way, and the force will decrease as it gets farther away. So we know that the field, in fact we're going to define this, the field is a vector. It's a three-dimensional vector, so it depends on x, y, and z. It's a vector symbol there. It's equal to the force experienced by the test charge. So the force on, I'm not going to put the on, we don't really use that in physics. The force experienced by charge Q at the same point, x, y, and z. And then we're going to divide it by the charge Q. So, if we take a very small test charge and put it at some place, the force it experiences divided by its charge gives you the electric field strength at that point, and the direction as well, because the force has a direction. All right, I think that's the simplest way of putting that. So the units of electric field are going to be units of force divided by units of charge, so we get newtons per coulomb for the units of the field. All right? And as the book notes, often we want to find what the force is given a certain field, so we solve for the force on Q. And we find that it's simply equal to Q times the electric field. And again, I'm assuming at a particular point in space. Okay. A point here. If the force is in the positive direction, we got, let's say, positive field exerted there. Let's see. No. If Q is positive, if the charge is positive, the force points the same way as the field. If Q is negative, then the force and the field point in opposite directions. There. So that means that combining with what we had before, the force on a charge Q. I should put some into the way. All right, I'm going to have two charges. Here's a big one. It's going to be a point charge, though, but it might be a large amount of charge. That'll be Q. And I want to find out what the field strength is at some distance r away from it. So I'm going to put my test charge, Q prime, out here. Okay, so let's make this a positive charge as well, but I want to make it a very tiny one so I don't distort what the field is doing. Okay, so the force exerted on charge Q prime is like that. They got the same charge, so they repel. Now, the magnitude is 1 over 4 pi epsilon naught Q times Q prime over R squared. And the book, weirdly enough, waits a long time to introduce this concept to you, but that's the unit vector in the radial direction, pointing away from the source. So r hat has a length of 1 and it points in the direction of the r vector. And it points, we'll put the source at the origin, so this points away from the source. Okay. Therefore, since the electric field equals the force, let's see, the electric field is equal to the force divided by the charge. In this case, that charge is Q prime. That's the force on Q prime divided by the charge of Q prime. And that's the force. Therefore, the electric field at this point is going to be force divided by Q prime, so 1 over 4 pi epsilon naught times Q prime over R squared, R hat, and I've divided out the Q prime. There. Now, if we look at the charges then, how the positive and negative works, you see that the field surrounding a positive charge points away from it. And it gets weaker with 1 over the field gets weaker with 1 over the distance squared. For a negative charge, the field points towards the charge. And so on. So keep that in mind. The field around a positive charge points away from the charge. The field around a negative charge points towards the charge, inward. All right, and that is the end of this lesson. Make sure to work through the examples of this. The math is actually pretty easy, but just getting used to the idea of which direction the field or the force points take a little bit of practice. Otherwise, it's the same kind of thing you've had with all other forces before.